In this video, we're learning how to compute the electric field from the gradient of the potential function. So we need a little bit of background on energy concepts. And in our picture, what we're looking at is a charge of plus Q moving from an initial point of A to a final point of B. There's an electric field there shown in the background, and that's exerting an electric force on this charge as it moves along the path. And we can see our little path increments. We call those dLs. Those are always pointing tangential to the path as we move from A to B. So as just a very quick review of these basic energy concepts, remember that the work done by a conservative force is equal to the negative of a change in a potential energy function. And the electric force happens to be a conservative force. So we put in a little more detail here, and we remember that work is the integral of F dotted into dL along the path. And at this stage, I've also put in the fact that the change in potential energy is just the potential energy at point B minus the potential energy at point A. But remember, the electric force exerted on this charge is given by QE, where E is the electric field. So we're going to sub that in. And at this point, I've also subbed in the fact that the electric potential energy is given by Q times V, where V is the electric potential. So on the right-hand side there, for our change in potential energy, we have a QVB minus QVA. And I've also replaced the electric force in the path integral with a Q times E. Now at this point, we can divide out the Q from both sides. And so we arrive at this fact that the path integral of E dotted into dL is equal to the negative of the change in the potential function. Now we can just solve for the change in the potential function, and we arrive at this useful equation. The change in potential is given by the negative of the path integral of E dotted into dL from the starting point to the finishing point. So now we want to rephrase this integral equation in differential form. So we're looking at a delta V, a cumulative change given by an integral, and that means the infinitesimal contribution to that cumulative change, we're going to call that dV, is just given by negative E dotted into dL. In other words, the interior of the integral. But now we can get into some more detail on what the electric field vector actually looks like and what the path increment vector looks like. And we're going to frame this in a three-dimensional context here, so just to be as general as possible. So there it is. I replaced the E with an X component times I hat plus a Y component times J hat plus a Z component times K hat. And I do the same thing for dL. So note there that each component of dL is just an infinitesimal step in one direction. So dx times I hat plus dy times J hat plus dz times K hat. And now we can explicitly compute the dot product here. Remember, that's just the sum of the pairwise products of the coefficients of each of these unit vectors. So I get a negative EX dx minus EY dy minus EZ dz. And now we have to use a concept from multivariable calculus. What we're looking at here is the total differential of the potential function. That's dV. And we remember the total differential is given by the rate of change in the x direction times dx plus the rate of change in the y direction times dy, and similar for the z direction. So that rate of change in the x direction, that's an x partial derivative of the potential function. The rate of change in the y direction is the y partial, and so on. So we immediately conclude that if we take the x partial derivative of the potential function, we get negative EX. We take the y partial derivative of the potential function, we get negative EY, and the z partial derivative, that gives us negative EZ. So now we're really close to getting a handle on how to compute the electric field components from the potential function, which is the whole goal of the video. So just moving the minus sign to the other side, we can now find all three components of the electric field by using partial derivatives of the potential function. Now, writing this all in vector form, we have that the electric field vector is given by the negative partial of V with respect to x times I hat, minus the partial of V with respect to y times J hat, minus the partial of V with respect to Z times K hat. But there's actually a better name for this thing that comes from vector calculus. What we're looking at is the negative of the gradient of the potential function V. So that symbol, the little triangle with the arrow over the top, that's the gradient operator, and it means you take all of the partial derivatives of that potential function and multiply those partial derivatives by the corresponding unit vectors. So that's the answer to the main question of the video. How do you compute the electric field from a potential function? The answer is you take the negative of the gradient of the potential function. And there's actually a really intuitive geometric interpretation to this idea of gradient. If I just focus on the direction of the gradient vector really quick, the gradient tells you the direction of steepest ascent of the potential function. In other words, the direction of this thing tells you which way do you have to point to increase the potential as rapidly as possible. But with a minus sign out in front, the direction of electric field is pointing in the direction of steepest descent of the potential function. In other words, which way do you have to point to go downhill as rapidly as possible? And this makes a lot of intuitive sense because we expect charges to naturally flow in the direction that decreases their potential energy as rapidly as possible. So now one last point about how this is applied in introductory physics. When you get to the upper division level, you're going to phrase all of your electrodynamics in terms of legitimate vector calculus. But in first year physics, we simplify this to always being a one-dimensional context. So we've done a ton of electric field integrals at this point, and we're always looking at the electric field as a function of distance from a charge distribution, usually along some axis of symmetry. So we're only looking at how it varies with respect to a single variable that we could just call r. Now in a one-dimensional setting, the negative of the gradient reduces to a simple negative of the partial derivative with respect to r times r hat, the unit vector pointing in that direction. And you can think of this as just aligning the I hat axis in the direction of r in order to simplify the gradient because it's just a one-dimensional setting. So that's really our practical result here. If we're able to calculate a potential function as a distance of r from some charge distribution, then all we have to do is take the negative of the r partial derivative of that potential function and then multiply it by r hat, and we have the electric field vector. So to put this into practice, we're going to work an example. And this example goes back to the video I made where I first introduced the idea of computing a potential function by integrating directly over a charge distribution, and I'll post a link to that video at the top. What we're looking at here is a uniformly charged ring of radius r, and we're finding the potential function at a distance of r from this ring and lying on the symmetry axis of the ring. So in other words, we're reducing things to a one-dimensional setting. Now, when we work this example, we arrived at this solution that v of r is given by q over 4 pi epsilon 0 square root of little r squared plus big R squared, where little r is the distance from the center of the ring and big R is the radius of the ring itself. Now, using our new idea about computing the electric field from the gradient of the potential, we should be able to compute the electric field at this location by just taking the negative of the r partial derivative of v, and then we can compare to our previous result for the electric field at this point. So in a previous video, we directly computed this electric field by integrating over the ring and using Coulomb's law. And I'll post a link to that video at the top as well. So let's get into this gradient business. E of r is going to be the negative r partial derivative, so negative del r of v of r. So I've got to take the little r derivative of this expression. Now we have a lot of constants hanging out in front. That's our q over 4 pi epsilon 0, and I'll move the minus sign out in front. And then we're taking the r derivative of a 1 over square root little r squared plus big R squared. Well, I could write that as r squared plus r squared to the negative 1/2 power. Now, taking that r derivative, I'm going to use the power rule here. So I'm going to bring down the negative 1/2 out in front, subtract 1 from that exponent, but don't forget about the chain rule here. So the derivative of this interior function gives us another factor of 2 little r. So when I pull the negative 1/2 out in front, that's going to cancel the existing minus sign. So I'm just going to write q over 4 pi epsilon 0. And then I have a 1/2 and a little r squared plus big R squared to the 3/2. And then the chain rule, again, produces a factor of 2 little r. So that 2 is going to cancel the 1/2. And we arrive at an electric field as a function of r of q times r over 4 pi epsilon 0 times little r squared plus big R squared to the 3/2 power. And this agrees with the previous result that we got by using Coulomb's law and integrating over the ring. So we've successfully rediscovered our electric field by using a partial derivative of the potential function. Now, to make our answer a little more complete, we can state this as a vector. So the electric field vector as a function of r is going to be this expression for the electric field magnitude multiplying r hat, which in our picture is in the plus x direction. Now, to wrap things up, I want to point out, why would we want to find electric fields this way in the first place? Like I mentioned, we already computed this electric field in a prior video by directly integrating over the charge distribution, chopping it into little dq's and applying Coulomb's law. But the main point of the potential formulation is that the potential is a scalar function which in general makes it much easier to compute potentials around charge distributions than it is to compute electric fields. Because remember, the electric field is a vector, and if you're computing electric fields around a charge distribution, now you have a vector inside of an integral, which in general is not an easy thing to deal with. So the whole point of this formulation is that we can now compute potentials at any point in space. And then to get the electric field, which is the thing we're really after, all we have to do is apply the gradient. We take the negative of the gradient of that potential function, and we've got the electric field. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.